¿Dónde?
Ahí está.
Sí. Sí, ahora está. So it's a great pleasure to have Carolina with us once more. Unfortunately, the last class. But we're very happy to have her, and we hope that in the future she can be here in person to meet
like
us, because it's not too far from Brazil. So please, Carolina, the floor is yours.
Okay, thank you. So the last things that I wanted to present and discuss was, now that we know all the analytical modeling behind resonance theory, I wanted to discuss visualization theory, how we visualize our results, and some applications to the planetary case. So until now, everything that we discussed was from an analytical modeling, but now let's imagine that we cannot have an analytical model of what we want to study. And so we will run simulations, n-body numerical simulations, to try to construct our resonance structure and see what we can learn from that. So what we do is we choose a representative plane that normally we can do it by choosing the actions of the system, let's say J1 and J2. So we generate a grid that will be our initial conditions, and we integrate each of these points over at least one orbital period of the slowest angle in the system. And so we vary two parameters, keeping the rest of the angles, for example, fixed. And we keep track of some dynamical quantity that we will use to visualize our results. And then that quantity we will color code it to see the outcome of our results. So as an example, we can have the variation of the semi-major axis, or the eccentricity of the orbit, or the MEGNO, which is the mean growth of the orbit, or there are plenty of other dynamical quantities that we can keep track of. And each of these indicators have their own pros and cons, but we can understand the behavior of our system by analyzing these results. And so, for example, here I show you how we would do it. We would perform the integration of, for example, one of these initial conditions. We plot our semi-major axis as a function of the time, or the eccentricity, and we see how much some of these quantities vary, and then we color code it. And so we discussed the Hamiltonian of the pendulum, and we know how the level curves of the Hamiltonian would look like. We know that we have our oscillating part, we have the circulating part, and we have a separatrix between both kind of motion in the action angle variables. And so we know analytically what is the result that we have. So now imagine that we divide this plane in a grid of initial conditions, let's say 100 per 100, and we integrate them, and we plot the variation of, for example, the eccentricity. And so we see basically the different colors. We see in yellow, where we have large variation of the quantity that we're plotting, and we see that here we have different motion than the yellow one here. And so we can, if we were not able to generate an analytical model, with this idea of dynamical maps, we are able to visualize so even if we are not able to explicitly obtain the phase curve of the Hamiltonian, we are able to estimate the location of the main points, which will be this one here and the fixed points that give us the separatrix. And we can do the same for example, the circular restricted three-body problem. So a star, a planet, and an asteroid, and we saw this last time. We plot the eccentricity over semi-major axis, and we have the pericentric branch, and we have the separatrix of the motion. So inside here, we will have the oscillating part. And when we divide this plane in a grid of initial conditions and we integrate, we plot the variation of the eccentricity, and we see that we obtain the same features. So here we see that there is something happening here, which is the separatrix, and we see that with very small variation of the eccentricity, we get the pericentric branch. So we can estimate the main features of this resonant system. So here you can see that near the separatrix, all the colors are similar, and there is not, like here, a very sharp line for the separatrix of both motions. So what we did with Jérôme Dagan, he did one mini course, I think last semester, we chose to analyze how we could produce sharper separatrix in a dynamical map. And so we decided to define a diameter metric, which is the diameter of an orbit. So here, each element represents the amplitude of the considered action. And so you can see that the diameter d is a function that increases in time, accumulating positive scalars along the orbit, the complete orbit. And this thing is analog to the variation of the semi-major axis or the eccentricity that they showed before. So we use this to analyze the behavior of the D metric of a low-dimensional model, like, for example, the pendulum, as we discussed for some time now. And in the action angle plane, we have, once again, the cat-eye typical structure. And we plot the landscape of this metric D that I showed you before. So for a fixed value of the angle here, we plot the landscape of the D metric, and you see for the action, the positive values of the action, we see that the value of D linearly grows within the libration domain. But once we reach the separatrix, there is a sudden loss of the regularity of the function, the metric D. And after this, after the crossing of the separatrix, we see that the metric decreases monotonically. So there is a sudden loss of the continuity of the D function when we cross the separatrix, and of course, D is not differentiable in E equal to 0, and of course not in the separatrix because it's not even a continuous function. And this, of course, is symmetric for the negative values of the action. So the important part of this is that the D metric encapsulates important information on the regularity of the function rather than in its final value. So what we did was to introduce the second order derivative of this D metric given by this quantity right here, and we computed the derivatives using the central differences. And so in our grid, we will compute this value here, for example, in a red cross, by having the values of the the points in the side and the points on top and in the bottom. And so now if we plot a heat map of our diameter, and we once again compute the landscape of now the second derivative, we get something like this. So once again, we see that the landscape of the second derivative reacts like a Dirac pulses, both in the separatrix and in the value associated to the fixed point. So as you can see here in the vicinity of the separatrix within the libration domain, we see that the color is so the D metric takes similar values inside than in the separatrix, but if we in the landscape here, we see that the values should not be similar. So we have very different values corresponding to a separatrix. So what we did was once again apply it to the planetary case in the application of the two-body problem. And here you see the delta semi-major axis, and here you see the second derivative of the delta semi-major axis. And so here you see somehow complementary that here we have. So we can tell that here we have the separatrix, but here we can see it sharply. And we can see that there are these Dirac impulses and the loss of the continuity of the D metric. And so we see in the delta map, we see the important features, and in the segment with the second derivatives, we are able to very sharply recognize the separatrix. And so last time we spoke about resonance overlap, and we were able to give a resonant overlap condition in terms of the actions of the system. And so right now I wanted to go back to the quantities that we know in a planetary system that are, for example, the semi-major axis and the eccentricities, which are somehow the actions of the system. And I wanted to show how this resonant network looks like. And so we see that the 2-to-1 mean motion resonance is isolated, but then we see that all the other mean motion resonances begin to overlap. And so one initial condition can be simultaneously in different mean motion resonances at the same time. And so if we plot a dynamical map, we can see the same structures appearing. We see this is the variation of the eccentricity. And we see that we have the 2-to-1 mean motion resonance isolated. We have the 3-to-2, the 4-to-3. And then beyond this semi-major axis, everything becomes chaotic and we cannot distinguish anymore the individual structures. And this is because of the overlap. And you can also see some other structures that we can distinguish in the backward, in the backwards. So here we see some second and third order mean motion resonances that we can also distinguish from these dynamical maps. And so now let me apply this to a particular case, which is the 3-planet case, which is not so easy to model analytically. And so what we did was to choose a grid of initial conditions, but this time is the ratio of the mean motions. And from last time, we spoke that these quantities, the mean motion ratio, give us the commensurabilities of the mean motions. So in this plane right here, we will see in this part, in the top left, we will see the interaction between 3 planets, but we will see what happens when 2 of the outermost planets are closer together and far away from the innermost planet, which is closer to it. And in this case right here, we see the opposite situation. We see the case where 2 planets are closer together, the innermost 2, and closer to the star, and the outer planet is further away from the 2 planets, from the innermost ones. And in the diagonal, we see the case in which the 3 planets are equally spaced. And so we select a mass for the system, and we integrate our initial conditions, and we get a map like this one here. So this expression, SHA1 and 1, SHA2 and 2, SHA3 and 3, give us the condition for a 3-planet resonance. And so let's say that SHA3 is equal to 0, so we will be able to describe with vertical lines the commensurabilities between N1 and N2. So we get the commensurability, the mean motion resonances between planets 1 and 2, so innermost and middle. And in the horizontal line is the equivalent to have SHA1 equal to 0, so we have the mean motion resonances between the middle and the outer planet. But the things that appear in the map that are not vertical or horizontal are the combination of the 3 planets, and we can distinguish them for different. For example, here we see first-order resonances, 2 planet first-order resonances. We see that they have a separatrix that we can distinguish and plot, but second-order resonance do not show a separatrix, a liberation domain in this plane. And the same happens with the resonances between 3 planets. Here we can see the separatrix of a 3-planet resonance, but this one is 0 order, but a first-order 3-planet resonance, we cannot distinguish the separatrix. So these maps is telling us that all in this part, in the red part, we are getting overlap. And so in these parts, we are not, and initial conditions will not survive for much time. And if we plot for a different mass, we get a map like this. This mass is way smaller than the ones that we use for the other plot. And this plot right here is the second derivative of the same quantity. So the quantity, that the diameter of the semi-major axis, as described with the metric that I showed before. And here you can see that we can distinguish much more structure in the background than we can do in this map right here. So these 2 maps are exactly the same, but this one is applied, in this one we applied the second derivative instead of the metric, the D metric. So we can see that there is some benefits of using one over the other. And so let's discuss to finish the course some applications of the real life 3 planetary systems. So as we discussed in the first day, we know that planets are formed in a nebular, in a protoplanetary disk that comes from the formation of the star. We know that the planets carve a gap, and so they form gaps and rings in the disk, and we end up with a planetary system. But it was only in 2015 when the first image of a protoplanetary disk was observed, and it's the image of HL Tau. This is the first protoplanetary disk observed. And so here it was for the first time that we were able to see that probably the gaps that are observed right here are the ones that are carved by the planets. And only in 2018, we were able to observe planets inside these gaps in the protoplanetary disk. There are not many systems with planets and disks observed at the same time by now. So I wanted to show you what we can do with a dynamical analysis to try to understand what is happening in nature in these disks. And so for that, I wanted to discuss the case of HD163296, which is this disk right here, which has 2 rings and 2 gaps. And the thing that I will discuss right now is this thing right here. So this is a crescent shape that is observed in the first gap. And so this system it has an extended disk of about 1,000 astronomical units. And in these 3 gaps, there are supposed to be 3 planets of around a Jupiter mass at these distances right here. And observers are able to measure the depth of the gas depletion and of the CO. And so we will use this for our dynamical analysis. So the thing that we want to understand is what happened with this crescent shape. This crescent shape right here is supposed to be in the L4 position of the planet in this gap, but the planet in this gap is supposed to be at 48 AU, and the gap is at 55 AU. And if this structure here is in the L4 point of the planet orbit, it should be at the exact position of the orbit. So if just to remind you, the L4 and L5 points are co-rotating orbits with the planet that are stable locations. So if it was in the L4 position, it should be at exactly the same orbit. And the other thing that was not able to be explained before is that the depth of the gap that it's measured in CO, it's much shallower than what a Jupiter mass planet would produce. So what we did was to perform hydrodynamical simulations with 1 planet, a Jupiter mass planet, and 2 planets with lower masses. And we computed the depth of the gap that each of these systems would produce. And we compare it with the observation, which is shown here in black. And so basically what we see is that if we have 2 lower mass planets, the depth of the gas is much in accordance to the observation than what we would have if we had a Jupiter mass planet there. And you can do the synthetic, you can produce a synthetic observation and compare to the real observation. And if we have 2 planets in this gap, we see that there is very good agreement between the synthetic observation and the real observation. But the interesting part, in my opinion, comes right now from the dynamical analysis, because what we did was to place the planets way back in time in a further configuration, and we know that the planets interact with the disk, and so they migrate in the disk. And so we placed them outwards, we made them move because of the presence of the disk, because of the planet-disk interactions. And here in dashed lines are the positions where we say that the planets are right now to be able to reproduce the observations that I showed you before. And we see that there is a point in time, which is around 1 million years ago, 1 million years before, after the beginning of the simulation, where all the planets can cross the current semi-major axis at the same time with an eccentricity that is not so high. And because of that, we see that the planets are in mean motion resonance, and we can compute the 3 planet angles between them. And because we know that this crescent shape right here is supposed to be in the L4 position of the planet, we can compute the position of the angles in the plane, in the orbit. And with this dynamical analysis, we can now tell the observers, okay, so point in these exact positions, so we have the angles in the orbit, and tell us if there is really planets in that orbit. So I wanted to show you this because I think this is a very practical way of applying a dynamical study and combine it with observations to have a very precise and quantifiable solution. Another application is what happens after the dissipates. And so we can understand what happens to the planets after the disk dissipates by observing what's happening now. So in the gas-free stage of the evolution. And so one of the things that we can learn is something that I mentioned before when I told you about the discovery of Neptune. That is transit time invariation. So basically, this is a technique for observational technique that is used to infer the existence of non-detected planets by measuring the non-periodicity of the transit. So if there was only one planet transiting a star, we would see a really periodic orbit, also a very precise transit. And if there is another body in the system, we can detect a variation of this transit. And so this allows us to confirm the presence of non-transiting planets, so planets that we are not able to see, and constrain their masses or the eccentricities. And this effect is enhanced when we have mean motion resonances in the system. And the important part is that the amplitude of the signal of this variation depends on the distance to the resonance, and this distance is something that happens during the formation of the system. So if we understand the distance to the resonance and we can relate it to the observations, we can maybe say something of the formation of the system. And so to make it more clear what the transit time invariation is, imagine that we have a system of a star and only one planet, and that we will click a timer each time that the planet passes in front of the star. So now that the planet passes in front of the star, we see that we will mark here, and every orbit, it will happen exactly at the same time. But say that now, instead of only one planet, we have a second planet that we don't necessarily need to see. In this video, we see it, but we can also not see it, and it will act in the same way. So we will mark each time that the innermost planet passes in front of the star. And here you can see that it is not as periodic as before, because now there is a variation in the time of the transit. So with these variations, we are able to infer the presence of a non-transiting planet, and this will help us to increase the amount of planets that are detected, and depending on the variation, we can infer the mass of the non-transiting planet as well. And so
I'm sorry, this would work also if there were other two planets. Can you deduce how many there are?
No, because, well, it depends, but probably you will see the combined signal of planets.
Okay.
So normally what you would see is that you would have like the light curve, the brightness of the star will be blocked because of the planet. And so you will see something like this regularly if there is no other planet. But instead, if there is another planet, you will see that the light curve begins to shift. And so here you can infer that there is another object. And another way to study the outcome of the formation process is what happens with the after the disk, the planet disk interaction phase. So as I said before, when we have planets in the disk, we know that the planets should migrate because of the presence of the presence of the disk. So what we can do is to make them migrate and see the final configuration and infer how was the migration when there was gas in the disk. So we place the planets we pick the mass, we pick the semi-major axis, the eccentricities, the angles and everything, and we make them migrate. So we see that the mean motion ratio between both decrease, the semi-major axis decrease until at some point they reach the commensurability, so they get stuck in the 2-to-1 mean motion resonance. And in this moment, we see that the eccentricities grow and the resonant angles begin to librate altogether. And so if this, yeah.
There is another question.
Yeah.
Can this effect also happens when you have a single planet very close to its parenting star, some Mercury perihelion procession type of things maybe, or does it necessarily have to do with the existence of other planets?
The transit time variation, you mean, right?
I think
yes.
it's Victor asking. It's Victor asking.
Yeah.
Yes.
Yeah, so no, because like normally, so you would try to see so nowadays you apply the transit timing variation technique to planets that are outside, so you don't really know the eccentricity of the orbits, and so you would not see this thing of the getting closer to the periastron or not, because like normally you assume that the orbits are circular, and so what they do is afterwards, so if they detect the variation in the transit times, then they fit the eccentricity. But if there is this variation, it will be because of another planet. I hope it answers the question. And so coming back to this, so once we have so we make the planets migrate, and they once they get captured in the resonance, we see that they don't go away. So if this is the typical outcome of planet formation, we should expect that if we plot all the period ratio of all the planets that they are discovered in multi-planet systems, we should see peaks in the exact commensurabilities. So this is what we should see if the planet disk interaction was leading the evolution of a system. Instead, what we see is this. We see that the period ratio distribution is all over the place. So we see that there are a lot of planets that are not in exact commensurability. And in fact, the systems that are in commensurability are not in the exact position, but they are shifted a little bit away. We studied a little bit what happens with with planets in these peaks, so near the resonance, but not exactly in the resonance. Once again, we perform numerical simulations. We mimic a disk that has some surface density and has some aspect ratio with different kinds of disks, and we apply a damping in the semi-major axis and in the eccentricity that come from nonlinear expansions. And what we get is that the planets migrate until they reach right here I show the commensurability, and you see that the planets come near the mean motion, and they continue to migrate like constantly. And so we see that for different masses, we reach different values of the offset, so the distance to the resonance. And normally you would say that this is the offset from the resonance, because here is the exact position. In this case is the 3 to 2. But if we plot the pericentric branch as we did, because we know we can do this for 2 planets, we can have the pericentric branch of the resonance for each of these masses, and we see that the planets are in fact following their pericentric branch, but each branch is different for different masses. So it's not that they are shifted from the commensurability, but they are following the pericentric branch. They are only away from the nominal value. And so here I show you the mean value in the observation. So here we are, I'm showing you the 3 to 2 mean motion resonance, and you see that the offset is 0.007 for the bigger masses, which is an order of magnitude lower than the observed value. And so what we did, so here we have the formulas that we use for this migration, but in Creswell and Nelson in 2008 performed hydrodynamical simulations, and they realized that the formulas need to be expanded, because we have to take into account what happens between the eccentricity and the aspect ratio of the disk. And so if we add these terms that they propose, because they are using hydrodynamical simulations instead of doing a linear expansion, what we get is something like this. So we see that instead of so before, the planets reach the commensurability and continue migrating constantly, but now what we see is that they depart from the commensurability. This effect is known as resonant repulsion. So if we go to so all of this is for the same mass. So we have only one pericentric branch, and what we see is that the planets migrate until at some point they go back and they use the same pericentric branch to escape the commensurability. And so if you see here, so this is for different values of the circularization of the orbit, but once again we are orders of magnitude away from the observed value. But if we change the masses of the planet, now we get closer to the observed value. And so this kind of analysis allow us to understand that the planets that we are observing in the exoplanet population are probably more massive than the one of our Earth, because they are showing offsets of these values that we are only able to obtain with realistic formulas for masses that are bigger than the Earth. And we can do the same for planets that are bigger, so high mass planets. Remember that those planets open gaps in the disk, and so they interact different with the disk. And so we need to take into account this fact that bigger planets open bigger gaps, and there is less material to interact with. And so there is a formula for the damping in the semi-major axis, but not for the eccentricity. And when we do that, we find something like this, which is similar to the case, to the first case that I show you for low mass planets, where the formulas are not very well, or very, what's the word? Like explicit, where we don't know how very good the interaction between the planets and the disk. But in any case, the observed value is in agreement with the simulation. And so from this kind of analysis, from the dynamical analysis, we can learn the masses of the planets. We can learn that we need to improve our formulation for migration for high mass planets. We can know, for example, that all the planets cannot have undergone planet migration because of the gas, because if not, we will have all the planets peaked in mean motion resonances, and that is not what we observe. A different application that we can do with that we can study dynamically is what happens once the disk is dissipated. So once the disk dissipates, let's say that we end up with a planet which is far away from the star, but in an elliptic orbit. And so each time that the planet passes nearby the star, it will deform, it will get oblated, it will lose orbital energy that will be translated to heat. And after many orbits, we can get planets that are closer to the star and end up in very circular orbits. And sorry. And what we did a couple of years ago was to study some particular systems that are in mean motion resonance, but they are connected via resonances. So they are in what we call a chain of resonances. And so once again, in this plane that I showed you before, the mean motion ratios of planets 1 and 2 over the 2 and the middle and the outward, we see again in vertical lines the mean motion of between the first and second planet, and in the horizontal lines we see the mean motions between the second and third planet. But the dashed violet lines show the resonances between the 3 planets altogether in the system. And so, for example, here we can see that the planets are not exactly in the intersection of two planet resonances, but they are shifted away following the 3 planet commensurabilities. And so what we did was, so here I show you the case of one of the system, which is Kepler 80. And we plot the offset, and we see that they follow this trend right here. And if we plot if we compute the periods following the 3 planet commensurability, we see the same trend that is shown here in black crosses. So we see that the shape that the departure from the resonance is following a trend that is governed by the 3 planet commensurability. And so once again, we perform simulations to see the complete evolution or like the long-term evolution of the system. And so we let the system migrate until they reach some time, which is represented in the vertical line. And after this line, we let the system evolve because of the tides of the star. So this process of losing eccentricity. And so we see that when the planets migrate because of the disk, they get close to the commensurability, the eccentricities get excited, and the angles begin to vibrate. So they are captured in the resonance. But when we let the system evolve because of tides of the star, the eccentricities decrease, and the system depart from the resonance in a long period of time. But the angles never leave the resonance, so they are still captured. In fact, they have less amplitude of the oscillation. And so we can try to understand with this type of analysis how are tides acting in the system. So we ask ourselves what happens if there are no tides in the system, which are represented by this circle here, and we don't see this shape that the planets are following. So the green one is the real system. So we see that if there were no tides, there would be no shape in the offset. So we can discard this. So we can say that there should be tides acting in the system. And if we can...
Sorry,
yeah.
for tides, you mean this shape fluctuations of the planets?
Yeah.
Okay.
So the deformation of the planet, which translates into a circularization in the orbit.
Yeah. Okay.
And so you can apply tides. So what we did was we applied tides to only 1 planet in the system, and we get this curve here. We apply tides in the first 2 planets, and we get this curve here. And so if we do that for all the planets, we see that the ones that much better the observation is when we apply tides to all the planets. And in fact, what we see is that once we do that and let the system evolve in time, then the system will continue to increase the offset, but following this same trend in the system. So from here, what we can learn is that we can apply the tides to all the, so probably in this kind of systems, the tides are acting in all the planets, and they would be acting in all the planets for all the lifetime of the system, and this shape is governed by the 3 planet commensurabilities. So yeah, so from this we can understand how like this shape in the offset, where it comes from. And the final application that I wanted to share is what happens after the dissipation of the gas, but when we are like, we don't need to be in resonance or close to the star so that we have tides from the star. We can be anywhere. So there is this theory that the planets that has low masses are following what we call a piece in a pod. So planets in a particular system have similar sizes or masses. So the mass of the system is like the same for neighboring planets. And if you have more than 2 planets in the system, there is a regularity in space and in distance of the planets. So here you can see, like, for example, this first system here, you can see that it's evenly spaced, and the circles, the size of the circles represent the size of the planet. And you can see that they are more or less the same, and they are more or less evenly spaced. And so you can see this in almost all of these systems. And so if we have a system that is not following this pattern, we can ask ourselves what happened to that system. And so this is what we did for one of the systems, because gravitational scattering can modify the final architecture of a system. So we studied this system right here, HD whatever. The main features are in this table here, because we see that we have an innermost planet, which is almost twice the size as the outer 2, and is further away from the second and third planet, and is way more eccentric. So we ask ourselves what happened. So maybe this system began or was formed in a piece in a pod configuration. So 4 planets, evenly spaced, similar masses, and maybe they underwent some kind of instability that led the system to what we observe nowadays. So we started our configuration like that. So we began with 4 planets instead of 3, similar masses, evenly spaced, and we let them evolve for some amount of time, just due to their gravitational interactions. And after some time, in around 10% of the simulations, we found that the 2 inner planets merged together, forming a planet with double the mass, similar to the observations, that is able to get so an eccentricity comparable to the one that is observed, and reproduce the system. And so once again, I wanted to show you this because there are like many different applications that allow us to understand what's happening in planetary systems that come from the understanding of the dynamical perspective. And so that was all that I wanted to discuss. So if you have any questions, please let me know.
Thank you very much for the great last lecture. So yes, let me stop here.